Hello students. So we'll do a quick recap. So in the last class we saw about sound waves. In that we saw longitudinal waves, categories of sound waves based on their frequencies, velocity of sound waves, factors affecting the velocity of sound. And then we saw about the reflection of sound. In that we learned laws of reflection. So today we are going to learn a new topic, that is reflection at the boundary of denser medium. So what is the meaning of denser? Denser means the density will be more. For example, you can take glass. So observe this image. In this image there is a longitudinal wave which is in the form of compression and rarefaction. There is a longitudinal wave which is in the form of compression and rarefaction. So this longitudinal wave travels and hits in a rigid wall. If you can see in this picture, this is a rigid wall. It exerts a force F. So the compression will exert a force F. So this rigid wall, according to Newton's third law, will give equal and opposite reaction. So the reaction will be minus F because the direction is opposite. So the compression traveling towards the rigid wall will reflect back as a compression but in opposite direction. So the direction of compression is reversed. If you see in this picture, the green color line is the initial compression. So after hitting the rigid wall, due to the opposite reaction, the green line, that is the compression, is reversed. The direction of the compression is reversed. So the next topic that we are going to see is the reflection at the boundary of a rarer medium. So what is meant by a rarer medium? If something which has a lower density is called as a rarer medium. For example, you can take air. So observe this image. So this is a longitudinal wave in which the longitudinal wave is in the form of compression and rarefaction. So observe here, this is not a rigid wall, it is a rarer medium. So be careful with it. This is not a wall, this is a rarer medium. So when this longitudinal wave travels, the compression will exert a force on the rarer medium. The compression will exert a force F on the rarer medium. So this rarer medium will have a very small resistance. So it will push back the compression. And then compression is reflected as rarefaction, and then the rarefaction travels from in the opposite direction, that is from right to left. So now we are going to learn a new topic, and that is reflection of sound in plane and curved surfaces. So there are two cases. If a sound reflects on a plane surface, what will be the intensity, and the sound when it reflects on a curved surface, what will be the intensity. First we will see through how does a sound reflect in a plane surface. So if you observe this image, there is an incident wave, there is a reflected wave, and then there is a normal. All this lies in the same plane. So this is according to the laws of reflection. As we know, the incident angle and the reflected angle will be same, and also the incident wave, the normal wave, and the reflected wave will lie in the same plane. So this explains the laws of reflection. And in this, the intensity of the reflected wave is neither decreased nor increased. The reflection of sound in curved surfaces. As we know, the intensity of the sound in plane surfaces do not change. That is, the intensity will be constant. But in curved surfaces, it is different. The intensity of the sound wave will change. So there are two cases. The first case, if the sound is reflected in a concave surface, and then the sound which reflects in the convex surface. So observe this diagram. This picture A represents the concave. You can see this is a cave-like structure. This is a concave surface, and the opposite of it is a convex. So if you see here, this B picture represents the convex surface. So we'll see one by one. When a reflected from a convex surface, the reflected waves are diverged out and the intensity is decreased. So if you see here, these are the sound waves. If I am going to produce this sound wave into the convex mirror, then it will diverge, that is, it will go out. So if I am giving an initial sound wave, it will come, hit the convex surface, and then it will diverge. Therefore the intensity will reduce. But in concave surfaces, if I am giving a sound wave, then it will converge and focus at a point. That converge means coming inside. So this sound wave will go, hit the concave surface, converge, and then comes to a focus point, and this is the focus point. So in this case, the intensity will be more comparing to the convex surfaces. So if you see this image, this is a parabolic hall. If you see itself, this is in a concave structure. So all the sound will focus at one point, so the intensity will be more. If you see this image, this is an elliptical hall. If I am standing at one corner and I am talking, that is, my sound will focus at one point, and that sound will be reflected to another focus. So this principle is used in whispering halls. We are going to see a very familiar and a very easy topic, and that is echo. So before going into the topic, we'll see a very short video.
Echo. You must have visited an echo point at a hill station. If you shout loudly at such a point,
Hello,
you hear the same sound
hello,
just after a little while. This sound is called an echo. An echo is the repetition of the original sound because of reflection by some surface.
So what is meant by an echo? The echo is a repetition of the original sound because of the reflection from some surfaces. So all of you would have experienced echo. So now we will see this topic in detail. So there are two conditions for an echo to occur. So the first condition is the minimum time gap between the original and the echo must be 0.1 second. Why? Because the persistence of human ear is a 0.1 second. That is, if you want to hear two sound waves clearly, then the time gap between the two sound waves should be 0.1 second, and that's why there should be a time gap between the original sound and the echo as 0.1 second. And the second condition should be the minimum distance required to hear an echo is 17.2 meters. So just consider this is a person. He should stand in a distance of 17.2 meters and then only he can hear the echo. If he stands less than 17.2 meters, then he cannot hear an echo. So these are the two conditions for hearing echo. We are going to see the applications of echo. There are enormous number of applications. We'll see some of them. So the first one is the bisonar or echolocating, which is an application of echo. Then the echo is the principle which is used in optic ultrasonography, and then echo is also used to determine the velocity, that is the speed of sound waves in any medium, that is air, liquid and solid. And now we are going to see an experiment to measure the velocity by echo method. So all we need is a source, a measuring tape, a sound receiver, a stopwatch. So now I am using a piston as a source, and then I need a wall to reflect the sound back. So they are placed in a distance of 17.2 meters because it is a condition for an echo to occur. So I am measuring it with a tape. And now I am a receiver standing adjacent, that is standing near to the source. As soon as I hear the original sound, as soon as I fire this gun, and this sound wave will travel and reflect in this bounce in this wall and reflect as an echo. As soon as I hear the echo, I will stop the stopwatch, that is I will start the stopwatch by initially hearing the original sound wave, and I will stop the stopwatch as soon as I hear the echo. And I will repeat this experiment to 4 to 5 times to get the accurate velocity of the sound. So how to calculate the velocity of the sound? There is a formula. So the sound pulse emitted by the source travels in total distance of 2d. Why 2d? Because first the distance is between the source and the wall, and then the distance is between the wall and the receiver. So it is 2d. So the time t is considered. So to calculate the sound, we have a formula called 2d divided by t. We are going to see about the application of a reflection of sound. So there are 3 applications, that is the soundboard, the ear trumpet, and the megaphone. So now we are moving on to a very important topic, and that is Doppler effect. So before moving into the topic, we will see an example. So if you see here, there is a train at rest, that is it is in stationary position, and it has a whistle sound. So if you hear that whistle sound, there the frequency will be same. Or else if you are standing in a station, and at that time if that train crosses you, when you and the train meet along, then you will hear a higher frequency of whistle sound. If the train goes away from you, then you will hear a lower frequency of whistle sound. So these apparent changes are observed by a person called Christian Doppler, who actually observed and invented the Doppler effect. And now we are going to see the definition for Doppler effect. So, when there is a relative motion between a source and a listener, the frequency of the sound heard by the listener is different from the original frequency of the sound emitted by the source. This is called as Doppler effect. So, now we are going to see the possibilities, that is the relative motion could vary due to the various possibilities. All we need is a source and a receiver. So in this picture, first we are going to see first possibility, that is the listener moves towards or away from the stationary source. So what is meant by stationary? That is, it will be in rest position. For example, consider this speaker. So these two speakers are at rest position, and he is the listener. First he moves towards the source, and then he moves away from the source. So if he meets at this point, he will hear a higher frequency. As he walks away, he will hear a lower frequency. So now we are going to see the second possibility, that is the source moves away from the stationary listener. As we know, stationary means rest position. So this person stands at a position. This ambulance, that is the source, is towards him. When these both meet together, he will hear a higher frequency. If the ambulance goes away from the person, then he will hear a lower frequency. And the third possibility is both the source and the listener move towards or away from each other. That is, the ambulance and the listener are moving. Both the source and the listener are moving. So if they meet at this point, then at that instant the listener can hear a higher frequency of sound. And the fourth possibility is the medium moves when both source and the listener are at rest. Hope all of you have understood the topics that I have taught you today. Thank you.